Hello everyone, my name is Debayan Bhattacharya. I am a PhD student under the Institute of Medical Technologies and Intelligent Systems at Hamburg University of Technology. I will be presenting my paper titled Self-supervised U-Net for segmenting flat and sessile polyps. In this slide, we would like to talk about the motivation of this paper. Colorectal cancer is one of the most prevalent types of cancer. It is the third most common cause of cancer in the US. Development of polyps in the colorectal area are precursors for the onset of colorectal cancer. To prevent polyps developing into cancer, doctors perform colonoscopy to check for the presence of polyps. Upon detection, doctors take the decision of whether to resect the polyps. A study has shown that early detection and resection of polyps can increase the survival rate to 90%. However, detecting polyps is not that easy. The appearance of polyps are very heterogeneous. As can be seen in the diagram, polyps appear in different shapes, sizes, and color. Furthermore, the morphological characteristics of the polyps change over time, and this makes analyzing polyps even more challenging. In other words, manual detection takes a lot of effort and are prone to errors. Therefore, computer-aided diagnosis systems, or in short, CADX, have been proposed. Such systems can assist in monitoring and increase the diagnostic capability of the doctors. CADX systems can be used as a secondary check. The core idea is that CADX system predicts the segmentation maps of possible polyps in an image or video. In doing so, it reduces the subjective bias that persists in manual screening. In summary, a CADX that detects or segments polyp can reduce the misdetection. However, despite the development of CADX solutions, misdetections are still a reality. In a recent study, it was found that 6% to 27% of polyps are misdetected. Additionally, polyps that are sessile and flat in appearance are even harder to detect. Sessile means that the polyps are immovable, while flat here describes the appearance of the polyps. These polyps are most likely to be missed by CADX solutions and doctors. As can be seen from the diagram, these polyps almost merge with the background and as such have very limited morphological differences in comparison to the non-polyp surrounding surface. To make matters more challenging, the polyps are small in size, that is, they have diameters less than 10 millimeter. All these factors make detection of such polyps very challenging. In 2021, Jha et al. From Similar Research Laboratory published a dataset called Quasir-Sessile dataset. This dataset contains an image of colorectal area with the corresponding segmentation mask. It is a collection of 196 images of colorectal area. Each image contains at least one flat and sessile polyp. All the polyps in this dataset have diameter less than 10 millimeter. And these images are a subset of the larger quasi-sec dataset which contains 1000 polyp images. Before we head on to the methodology, we briefly go through the related work in automated polyp segmentation. Prior works have focused on handcrafted features for polyp segmentation. However, these models have high false negatives. This is because the representation capability of handcrafted features is limited. The high variation in the appearance of the polyps and the background colorectal surface make such models perform poorly. In contrast, deep learning methods have shown promising results in segmenting polyps. Many authors have proposed new architectures to increase the segmentation accuracy of polyps. Some notable works are as follows. Brandau et al. Used FCN to segment polyps. Zhao et al. Used U-Net++ to segment polyps. Jha et al. Added residual and attention modules into U-Net architecture to increase the segmentation accuracy of their model. Fan et al. Proposed parallel reverse attention network, in short PRANET, that focuses on boundary cues to enhance the segmentation maps. In doing so, they show that their model performed better than the state-of-the-art models. A common trend in all these work is that all these models are trained in a supervised fashion, and only architectural changes are considered to improve the segmentation accuracy. A study by Jha et al. Showed that smaller datasets perform poorly in comparison to larger datasets. This is expected as the model trained with few training images tend to overfit on the training set. As such, it loses its generalizing capability. In summary, we would like to bring out three problems that motivated our paper. Number one, flat and sessile polyps are hardest to segment. We want to train a model that segments flat and sessile polyps better than models trained in a fully supervised manner. Number two, labeling is expensive. Generating segmentation maps in particular takes more time in comparison to generating classification dataset. Furthermore, if two or more people participate in the creation of segmentation maps, inter-observer variability exists in the ground truth labels. This adds uncertainty to deep learning model predictions. Therefore, we want to train models that use less ground truth labels but still segment accurately. Number three, quasi-sessile has only 196 polyp images, or in other words, we have a small label dataset. And as mentioned earlier, CNNs perform poorly on small datasets. So the question remains, can we make use of a larger unlabeled dataset to improve the performance of a smaller dataset? Or specifically, can we make use of the parent quasi-seg dataset to improve the segmentation performance of quasi-sessile dataset? The short answer is yes. Yes, we can get better segmentation accuracy with the same dataset. For this, we use self-supervision. Our work focuses on using self-supervised learning. To the best of our knowledge, this is the first use of self-supervision in polyp segmentation task. So before I can explain the methodology, I would like to briefly explain what self-supervision is. Self-supervised learning is a method of machine learning that makes use of unlabeled data. It is a learning method that can be placed between supervised learning and unsupervised learning. As shown in the diagram on the right, there are two steps in self-supervision. The first task is based on pseudo-labels or supervisory signals which we can generate without any help from an existing data. We train a neural network based on these pseudo-labels. This task that we make the neural network solve is called the pretext task, and this training is called the pre-training. There are various pretext tasks that can be solved. To name a few, in painting, randomly dropped out pixels, colorization of images, predicting relative spatial position of image patches, and predicting the transformations that have been applied on an image have commonly been used in literature as pretext tasks. After pre-training, we train a model for the actual task that needs to be solved. In our case, it is supervised training to segment polyps. This step is called the fine-tuning step. So why do we perform pre-training? Pre-training helps the neural network learn the underlying structure that exists in the dataset. Furthermore, pre-training helps the model build hierarchical representation of the world. We leverage the larger unlabeled dataset to improve the performance of the downstream task on the smaller dataset. In doing so, we become label efficient. That is, we need less number of labels to achieve better segmentation accuracy. In this section, we describe the methodology of our paper. We randomly picked 10% of the quasi-sessile dataset and made it the test set. From the table, that is 20 images. Of the remaining images, we split it into 5 folds of equal sizes and use a leave one out fold for cross-validation. To make a fair experiment, we remove all the quasi-sessile test images that are present in the larger quasi-seg images or the seg dataset. In other words, even during pre-training, we do not make our neural network see any images from the quasi-sessile test dataset. In summary, we use 980 images of quasi-seg dataset. We use 140 and 36 quasi-sessile images to train and validate our models respectively. As a pre-training task, we use in-painting. We randomly cropped out rectangular cutouts from the images and trained the model to fill the blacked out portions. The encoder of the model encodes the context of the image in this process. The context encoding helps the neural network make reasonable guesses for the blacked out pixels. By context encoding, we mean that the neural network considers the surrounding pixels of the black rectangle to fill it. While encoder compresses the image into a latent representation, the decoder uses this latent representation to fill the missing pixels. Below is our loss function that we have used for in-painting. It is a squared L2 norm. Here, capital F is a neural network model which we parameterized by the theta. Small x is the input image and m is the binary mask where the drop pixels has value 1 and retained pixel has value 0. The neural network that we have used for pre-training is a U-Net. Once our U-Net is pre-trained, we then train it for the downstream task, which is polyp segmentation. We use Tversky loss with alpha 0.4 and beta 0.6 found empirically. We use Tversky loss because it gives us a better trade-off between precision and recall. In other words, we can penalize the network more false negatives than false positive. We compared our self-supervised U-Net against 5 popular segmentation models. The 5 segmentation models we considered for this experiment are U-Net, Attention U-Net, R2 U-Net, R2 A-U-Net, and Res U-Net++. All these models have similar baseline U-Net structures with additional modules to enhance feature representation. For example, the Attention U-Nets have attention block at the decoder. R2 U-Net has a recurrent residual block where the residual part ensures that the deep network can be effectively trained while the recurrent ensures feature accumulation, and that ensures better feature representation for segmentation tasks. R2A U-Net is similar to R2 U-Net with the addition of segmentation with the addition of attention modules at the decoder. And finally, coming to the Res U-Net++, it has squeeze and excite blocks after every ResNet block at the encoder and attention block after every ResNet block at the decoder. All these models were trained in a fully supervised manner on the quasi-sessile dataset. In this slide, we give a description of our implementation details. All the models were trained for 65 epochs with a batch size of 4. For pre-training, the first 50 epochs are trained with a learning rate of 1 e to the power of minus 5 and the remaining 15 epochs were trained for 1 e to the power of minus 6. For supervised training, the first 50 epochs were trained with a learning rate of 1 e to the power minus 4 and the remaining 15 epochs were trained with 1 e to the power minus 5. Early stopping is used to prevent overfitting. Data augmentation such as random flipping and rotation is used. And image resolutions used are 192 cross 192, 320 cross 320, and 512 cross 512. Adam Optimizer with default parameters has been used for training. And finally, we use PyTorch as our deep learning framework. The quantitative results are shown in table. We use dice coefficient, mean, intersection over union, precision, and recall to evaluate the model. As we can see, self-supervision achieves considerable performance improvements over the supervised model. In particular, we see U-Net with self-supervision increases the dice by 0.29, 0.31, 0.32, 0.36, and 0.30 in comparison to the dice of fully supervised U-Net, Attention U-Net, R2 U-Net, R2A U-Net, and Res U-Net++, respectively. Similar improvements are observed in mean IOU, precision, and recall. Another observation to be made is the smaller dice and mean intersection over union of the larger models in comparison to the U-Net. The qualitative comparison of our U-Net is shown in this figure also. We see for both the images, U-Net with self-supervision is able to segment the flat polyps with great accuracy compared to the models trained with full supervision. Finally, we arrive at the conclusion and discussion of our paper. This is the first use of self-supervision in polyps segmentation task. Prior works focus on fully supervised approaches with modification made to the network architecture. We show that U-Net that is devoid of feature enhancement modules achieves superior performance in comparison to 5 segmentation models if trained in a self-supervised manner. We also see that models with more trainable parameters perform poorer than U-Net with full supervision. We believe this to be the case because models were trained on very less training images. Models with more parameters have higher chance of overfitting, and our experiments reflect this scenario. In conclusion, we believe that self-supervision is an important learning paradigm to make lightweight models generalize better. This is particularly important if we want to implement artificial intelligence-driven CADX in clinical practice, where computing resources are not always present. We hope our work will aid future research in this direction. We have the references here for you to see later on. Thank you so much for tuning in, and I hope you have a good day.